Now, today's topic is impact echo, and we've been supplying impact echo equipment at PCTE for a long time. Two I'd like to highlight is the Proceq PI8000 Pundit Impact. This is a impact echo test device and also a sonic echo pile integrity testing system. So it's a combined choice, good for general purpose impact echo and general purpose pile testing. On the other side of things, we've been working with Olson instruments for a long time as well, and we have their concrete thickness gauge too, and the impact echo accessories for their NDE360 and Freedom Data PC devices. This is going to be very suitable if you've got a specific job you need to do, or if you like to combine a broad range of different signal analysis-based tests. So we'll be talking impact echo in general today, but these are the two most current systems we have for this testing technique. And if you'd like to see it in person, do let me know. The QR codes go to the product pages for those. And just to give you a brief on what I will and won't be covering during today's presentation, this is specifically more of a theory and operational overview. It's not a demonstration of the devices or an instruction on how to use them. I find that the best way to get ready to use impact echo equipment is to build a strong understanding of its operation in theory, and then you're ready to start taking tests with the equipment and interpreting what you see based upon your theoretical understanding. But the best way to become a really good user of those tools in practice is to get the repetitions in person. So I'd rather, if you would like to see this equipment used or learn more about how to use it, we'd line up some time to meet and work in person than to specifically try and cover that during a video presentation today. I'm going to begin by talking about compression wave theory, one of the many forms of seismic energy that are transmitted when we strike or otherwise induce energy into a concrete structure or other material. Then I'll explain how impact echo testing works. And I want to specifically discuss as part of that what I mean when I say impact echo is a resonance test, but to sort of distance ourselves from the name, which impact echo is a little misleading. An impact echo resonance testing is more descriptive. And so I'd say resonance is the thing people don't know they don't understand the most. So I'm going to clarify that specifically. And the second topic that people maybe don't have a full understanding of is filtering, which they'll tell me every time. What are the settings for the filter? Is there a correct value for a filter? So I'll be going into some detail on filtering. Then we'll look at some different kinds of interpretation and impact echo data together, essentially the effect different kinds of geometry or structure will have on impact echo testing, and how can we can interpret different forms of defect or different geometric measurements we want to take with that system. And I'll just finish out pointing out how often we don't care about a single point, like you can see in the picture there, where the operator's just testing a spot. We tend to collect impact echo data on a grid or over a large area to compare results over that area. I'll talk about grid collection. Now, as I go, I do like to answer questions during webinar presentations when they arise. So please put them in the chat or send me or just unmute and ask your question when I ask for questions. It's more effective to address them at the time they occur to you. So to begin on the physics, compression waves are sound. You're listening to them now. They're able to be carried through gases and solids, and they're a compression and extension of the molecules in the material as we travel. And the sensors we use to collect impact echo data are sensitive to compression wave to sound energy. When we do an impact echo test, the very first thing we do is we press our sensor on the surface and we strike in some way the material to induce the energy for our test. Now that strike doesn't only produce compression wave energy. It's going to produce compression wave energy, shear wave energy, surface wave or Rayleigh wave energy. And the sensor, even though it's most sensitive and broadly intended to capture the compression waves, will be influenced in some ways by these other forces of energy. We don't need to concern ourselves too much with that beyond understanding that the simpler the geometry, the less interference we'll have to deal with. So in this case, for example, if we have a thin enough or wide enough section, that Rayleigh wave energy represented by the white triangles won't make it to its edge and reflect back to it before the compression waves have been captured and we've finished collecting data for our test. But in a smaller geometry, it becomes more important to be as far away from other sources of reflection interference as we can. So that's the energy format we're capturing, particularly compression wave energy. Other forms of energy we consider to be a source of interference. So just furthermore, there's other techniques we do during this testing. So for example, the most common ultrasonic non-destructive test is ultrasonic pulse velocity. That's also usually done as a compression wave test, simply because if we have a sending and receiving transducer, the energy is going to go from the transmitter to the receiver the fastest in compression wave, and it's more difficult to isolate that compression wave energy. The other thing is, from our strike source, the energy is omnidirectional, so sources of interference can occur anywhere around the region of the strike. Now, the impact echo test itself, it's a test of resonant frequency with some filters and controls to make sure that the resonant frequency we measure is being controlled by the thickness and how voided or clear our concrete element is. It's typically used on what we'd call a plate structure, like a wall or a floor, something broad enough that if I put my sensor in the middle of it, I'll mainly be testing a very simple geometry. The more complex our geometry, the more limited our ability to use impact echo to test it is. We particularly want to avoid using impact echo test devices in corners, in circular geometries, in very complex elements. But a flat element without too much, not too close to the edge of it, is the ideal test placed for impact echo testing. Now, if essentially consider us to have an infinite concrete floor, perfect geometry, and at that point, the result of the test is going to be controlled by the speed of sound transmission in that perfect infinite concrete floor and the thickness of it. So if you look at our test there, we have a frequency and we have a thickness. And the reason we can convert frequency to thickness is we assume or measure the speed of sound, the pulse velocity of compression waves during that test. Now, it's measured from a graph. Now, that frequency that we convert to thickness, it's measured from a graph of a frequency spectrum. So that hero image you see there with the red line, the tallest spike on that graph of intensity on the vertical axis and frequency on the horizontal axis, the machine has automatically picked the greatest intensity, so the strongest returning frequency signal, and that dominant frequency, the dominant resonant frequency, is what we have converted across to thickness using the speed of sound. Now, the big, most common jobs we do with impact echo, I've just sort of explained how thickness is completed, but what it gets deployed for, even more than thickness, is void detection, where if we have a structure that is close enough to our ideal flat floor or wall, and we test with impact echo close to distributed voiding or larger voiding or cracking or damage, it's going to be very sensitive to it. All of the ultrasonic or seismic techniques are very sensitive to voiding and damage. So mostly impact echo is deployed as a void detection tool that can operate from one side of a structure. So that's the most common application, though we also have some more specialized applications where it's used for void detection in more complex geometries, such as voids inside the ducts of post-tensioning or grout tubes in precast construction. I'm not going to go into detail of that today. This is more the general theory and the general application to monolithic concrete with potential voiding, or monolithic concrete where we're measuring the thickness. We do have some international standardization, but no local standards for impact echo testing. The most prominent standard is the ASTM C1383 standard. And if you read through an American standard, if you've ever looked at these standards, they're extremely prescriptive of what the test is, what instruments are used to collect the data, how that data is processed, and what outcome and information is recorded during that test. But they're fairly limited on interpretation, suggestions of how that information is to be used. So if you read through the C1383 standard, you'll see it's predominantly concerned with using impact echo for thickness determination. ACI, American Concrete Institute, also has the 228.2R guidance, which talks a bit more about its use in the detection of voiding, honeycombing, distributed voiding, cracking, and delamination. And that's both of these areas that I'll discuss during this introduction session today. So I've explained what controls our test, the speed of sound in the material, the geometry of the material, and any voiding or defects inside it, along with its thickness. Let's look at how we collect and complete our test. This is the classic diagram of impact echo. You may well have seen this before. And if you have seen this before, it's important to understand that, like all diagrams, it's maybe 70, 80% true. There's no diagram in the world that perfectly represents the complex interactions that are being illustrated. So in this case, the most misleading portion of this diagram is the representation where our impact echo test has a single echo, send echo off the flat surface and received by the receiving transmitter, receiving transducer. That's just not correct. And we can even see that when we review this time domain data. So this is the raw data we collect from the measurement. In that, we can see we have a repeating pattern here, a oscillation as the energy echoes inside that material multiple times. The other misleading thing is, in this diagram, is not only do we have a multiple reflection, the energy from that source, as we know, is distributed in a broad section. So we not only get returns from directly on underneath the point of strike, but a region that the strike influences around the impactor. So please understand that if we're using impact echo, we're not using a single echo. We are recording the repeating reflections, the undamped energy, which we can see in that oscillation, which is desirable in our raw data, our time domain data. The first processing step that is complete is a fast Fourier transform. So if we look at the chart here, our graph is voltage, which we can take as a measure of signal intensity, of how strong the signal is, versus time. So this is just like a microphone recording. The oscillating energy received, but it's represented in a way that we would hear. But the fast Fourier transform converts this time domain graph to a frequency domain graph. So we now have on the horizontal axis frequency, and now we've got amplitude, which is analogous to voltage, the intensity of the voltage, how much voltage is produced at the sensor, and the strength of the signal, the amplitude, are essentially very related to each other. So now, rather than amplitude over time with a waveform, we no longer have a waveform. The data is no longer time dependent, but it is pulling out the frequencies. And once again, our dominant frequency, our resonant frequency, is what we are taking as our result. So that, in our formula here, is the resonant echo frequency, F, and we multiply that by a shape factor. So this 0.96, that's just because we assume it's an infinite concrete floor or wall, 0.96, and then the speed of compression wave velocity, giving us that thickness. We divide by 2 just because the signal is assumed to take this far to travel down and return. So that's the basic shape of that formula, converting thickness to from frequency with an assumed or known compression wave velocity and a factor for the geometry. So how do we use that to find problems? The first way is we're going to see changes in how those reflections occur if something occurs. If we have a delamination or a void, and it is substantial enough to prevent the reflection of the signals inside a material, we'll get a frequency shift. So in this case, we have a shift from 3.5 to 7 hertz. As we change our thickness, our geometry, from the full half meter to a void or defect or void former, half that distance, 250 millimeters, into that element. And this is the basic way we interpret our impact echo data. We don't look at the shape of the frequency or time domain graph in detail, though we do consider that for when we collect our data and the quality of that data. But our main interpretation is what is the resonant frequency and how does the resonant frequency differ to the default case. And that's quite important, is why we often collect impact echo data in a grid or large numbers of tests, is we want to have a typical situation to compare the rest of our output to. As I said, you really do need to be aware that all these little quickly sketched diagrams and the name impact echo don't capture the complexity of the test. So in this example, this was a simulation of impact echo, the intent of which was to show the effect of a tighter geometry on an impact echo test, in which case we can see that the result of the impact has broad amounts of energy, and also that red ring is particularly that surface wave reflection from the strike, and that comes back and reflects through the point of measurement as well once we limit our geometry and we get too close to the edges. So it highlights that what we're measuring is better represented by a model like this than by your simple sketch illustrations. And that if you do get a constrained geometry, you do need to be cautious of its influence on your test. As a general rule of thumb, I like to be a good 20 centimeters or so from the edge of a typical floor 250 millimeter type element or typical 250 millimeter, 150 millimeter thick wall. And if I get a thicker geometry like a beam or a column, I like to be further away again, maybe a good 300, 400 millimeters, just to limit the influence of these reflections from the edges affecting my test. So I've spoken to you and I've shown you the Fourier transform from time domain to our frequency domain chart. Now, show of hands or comments in the chat if you're able to do so. How much understanding do you have of how frequencies are presented in a chart of frequency versus amplitude? Oh, yes, Don. Can you hear me? Okay, if you don't mind, I'll mute the audio because I can't hear you, I'm afraid. So again, this chart is our chart of intensity of signal versus amplitude. It's the main chart we review and interpret for impact echo testing. And if you want to look at this chart and understand it, the best model for it is simply a piano keyboard. We have our lowest frequency outputs on the far left-hand side, and our highest on the control, yes, frequency vibration analysis university will certainly get you further along. It's very much, if you've done signal analysis, or my favorite is done some audio recording or musical electronic music work, you'll have a much better understanding than if you're just trying to look at these charts without that context. Thank you. But to get onto this chart, the best model is with a lower frequency on the left, like the low notes of a piano, and a higher frequency on the right, like a higher pitch note on the right-hand side of our chart. Further to that, we also need to capture only the frequencies we care about. So if you look at this chart, we can see we go all the way from 1 hertz on the left to 25,000 hertz on the right. But not all of the energy from our impact is sound. Some of it is effectively motion, wholesale vibration of the sensor or the concrete itself up and down, which will be detected by the broadband sensitivity of our particular systems. So we actually want to use what's called filtering on this chart. Particularly, we just don't care about the lowest frequency content because that represents motion, not sound transmission. And there's a point above which we don't care about our high frequency, but it won't influence our test very much. So we're mainly concerned with limiting this low frequency energy during our test. And the way that we limit this low frequency energy is we filter our data. This is again where that signal analysis or musical recording background becomes valuable, is when we talk about different kinds of filters. So the purpose of a filter is to remove from the measurement we take some of that frequency content, to do exactly as I said, ignore the lowest frequency signals that would be caused by the motion of the sensor or the concrete structure under the strike, and provide us only the frequencies that relate directly to the geometry, the thickness, or the defect detection work that we're doing. And if you look at your PI8000 software or your CDG software, there's going to be a couple of filters. You'll always have access to a high pass filter in impact echo devices, and you'll also have the ability to choose a low pass filter, or with some of the Olson equipment, because they're very flexible, they'll also offer band pass filtering. So the high and low pass filters are specifically about allowing the frequency that passes. So a high pass filter passes high frequency and stops or attenuates or reduces low frequencies. And the low pass filter does the opposite. It passes the low frequencies and it attenuates, reduces, stops the higher frequencies. So with impact echo, what we want to do is we actually want to attenuate our low frequencies. So we use a high pass filter as the main tool for our processing. Now, a band pass filter is a combination of both. It gives a band which it passes. So no frequency lower than its low boundary and no frequency higher than its high boundary, but the frequency in the middle, essentially a portion of the keyboard in the middle. And a band reject filter is going to be the opposite. It will only allow frequencies below its lower frequency or above its higher frequency. There's very little case you would use a band reject filter in this application, but you would use particularly a high pass filter, or perhaps a band pass if there was some reason to ignore results of very high frequency, maybe some sort of interference on your signal. Now, so just to illustrate further how this works, our high pass filter, the low pass filter is marking in red, so attenuating or removing the higher frequency results on our keyboard model. The high pass filter, the one we'll use for our impact echo testing, is chopping off the lowest frequencies, the deepest frequencies, marked in red. Band pass is a combination of both, chopping off frequencies below and above the white pass region. And the band reject is the inverse, allowing the low frequencies, attenuating all of the frequencies in between the two set points, and allowing through the high frequencies as well. So again, rule of thumb with your impact echo testing, the frequency we care about tend to be somewhere above 500 hertz. So a good just sort of general setting would be a 500 hertz high pass filter for impact echo testing. If you're testing to a reasonably thick element, if you're just doing plate testing like 150 millimeter thick, it may be appropriate to go as high as 2 or 4,000. If you're doing relatively thin segments, 150 to 150 millimeter, 250 millimeter sections. So that would be an alternative for slightly more constrained testing regions. Now, just to illustrate this in a little more detail, I'll just make sure the sound's coming through. 1 second. Here we are. So I'll just restart this video and I'll let you hear the influence of each. So on my system here, I have a high pass frequent filter set, and I'm going to be using the high pass filter to attenuate the lower frequency. So it's going to start out sounding very buzzy, but with quite a deep sound to it. And as the high pass filter increases, it will become buzzier and buzzier as all the low frequencies are removed from the result. Almost getting clicky, very high frequency sounds with the high pass filter increased. And then as we return to unfiltered, you'll have that lower frequency result, a less buzzy sound. I'm now going to set it to a low pass filter, so we'll be attenuating higher frequencies. So this will remove the buzziness from the result. So see, that's got the buzziness and the lower frequency sound, but as we return towards the filters, as we close that filter, only the more mellow, lower frequency sound will be detectable. So that provides a demonstration of each kind of filter in the context of filtering sound. Your impact echo data, when you see it, is going to be shown as a combination of a time domain chart. So that's in the green here, the lower chart, and the frequency chart, the fast Fourier transform spectrum. What we are looking for in a good impact echo test is firstly going to be a period of silence, because that means the sensor before the strike is receiving no input, and then when the strike occurs, the sensor detects that and records it. Whenever you're recording sound or signals, it's very important that your waveform doesn't go below or above the maximum of your chart. So we can see in this chart, we've got a repeating signal, but it hasn't gone below the lowest point on the chart or above the maximum point on the sound chart. If it did so, that would be called clipping, and it would ruin the test. It has the effect of essentially chopping off the result. So if I was to have an inappropriately set input gain on the results, and this was the minimum and maximum of the chart, what happens is the peak, positive and negative, of the sound results get chopped off and flattened. This is called clipping. You've heard this if you turn your speakers up too much on a sound system, as it goes all crunchy and horrible sounding. So if we're going to be doing frequency analysis on this result to overgain, to push our input above 100% or below negative 100% of the scope of the test, ruins the result. So first sign of a good time domain, a sound wave chart, is we don't go above or below the top of the chart, and our repeating frequency peaks don't flatten off, go clipped by the influence of too much gain, along with a period of silence followed by the signal arriving. The other nice thing we have is a clear oscillation, so that repeating result where we oscillate, and the slow attenuation, the loss of signal, sort of forming an almost funnel shape on that test. So that's a really idealized, perfect frequency result. A sound domain result, where we have a period of silence, we have an oscillating measurement, and a sort of return back to the 0 point of the measurement as the signal reduces in intensity over the time it was recorded. And the result of this really clean, really nice sound input is a very clean signal peak. So in this case, we've got a 12,000 hertz frequency relating to a 90 centimeter thickness, essentially a very thin test, and it's so clean that it forms one big clean spike. You'll find that real impact echo results are perhaps not quite as clean. They may have, just because reality is a little bit less tidy, sort of a mountainous shape where there's signal frequency energy before and after, but there's still a clear signal peak elsewhere on that chart. Just to show you how we would use filtering with real data, I wanted to show you a unfiltered result on the top of this image and a filtered result on this image. So in this unfiltered result, we can see that it has detected a frequency of around, oh goodness, about 10 or 20 hertz, extremely low frequency, well below that frequency that we would want our filter to be placed at. And in order to understand where that super low frequency energy comes from, I'd like you to look at this recorded slope to the data. If you think of it in context, it's actually a extremely slow motion, so 10 hertz, so 10 oscillations per second, captured for a very small number of microseconds. So that's why we have an extremely pronounced low frequency peak on our data. Now, we could try and perfectly control the physical environment so there was no low frequency vibration at all on our sensor. That would be one way to eliminate this problem, but it's not practical. So instead, we'll use the digital high pass filter to convert our results, which on the sound domain chart look almost identical, if you see here. But what we've done is we've applied that filter, this case about a 2,000, 2,500 hertz filter here. So we can see right at the point of that filter, there is no remaining response. And then, so all of this information here has been removed. And now that oscillation has been flattened out. It remains locked on 0, and our signal attenuates back to 0, returns to 0 after the energy is applied to the test. And we can also see that we now have this tiny little frequency response here on the previous chart is now clearly the result of our test. And we can see this is an order of magnitude lower. 0.01 is the peak of this chart, and this is 0.001, but that is our result. That's our dominant frequency of about 8,000, 9,000 hertz, correctly captured because we've told it with a high pass filter to reject the frequencies below that 2,000, 3,000 hertz point and correctly provide us with a single dominant resonant frequency over the range of frequencies we care about to measure a thickness. So some rules of thumb about where you can safely test and where you can't test with impact echo. So it's very much about finding details within the concrete. So we can't do anything too thin. So first thing, by within the concrete, I mean, if you have a slab on ground and you have a suspended slab, because of the way we filter and how we take the data to an impact echo test with its filtering and processing and collection, they will functionally look the same. So a thickness test of a slab on ground and a thickness test of a suspended slab with impact echo will have the same result. We're not able to tell anything about the support conditions, the subground conditions of concrete with impact echo. You can't go too thin. So the boundaries on the PA8000 or the CTG2, they're going to be somewhere around 80 to 100 millimeters minimum thickness. But there is specialist impact echo test hardware that can go thinner, maybe absolute minimum, about a 50 millimeter minimum thickness, below which we'll no longer be able to use impact echo to test. We do need to test on a uncoated surface, ideally. If we do have a coating, it would have to be fairly insubstantial and very firmly bonded. So essentially it just acts as part of the system. If we have a delaminated or thick or rubbery coating, we can't complete impact echo testing. We certainly couldn't do it over carpet or anything like that. We need access to the solid concrete to do impact echo testing. And the geometry does need to be relatively straightforward. So I sort of highlighted here, you know, a really solid coating, sure, maybe. We can't get too close to our edges because the geometry is too complex in the corners for us to test. And we want to avoid things like where we have thickenings or elements that are more difficult. I also would like to highlight that if we have a delamination, we're going to be testing the thickness to that delamination or the influence of that delamination on the test. We're not going to know anything about what's happening beneath that void, beneath that defect. Impact echo stops at the first break, so a delamination or substantial void. We can't see through it, we can't see behind it, we don't see into it, we see what's happening up above that defect. And again, so you've got that sort of 50 millimeter limit for specialist and about 80 to 100 minimum thickness for general testing. Your maximum is going to be around 1.5 meters in very simple geometry, something like a big foundation block, but it's not appropriate where again the geometry things, and can't do anything much in circular or more complex geometries. The way the resonance and the frequencies occur in that is more complex than the interpretation we're using. When we do complete our test, I've only spoken about the sensitivities and the frequencies. It's worth mentioning that the way we hit the surface as part of impact echo testing actually controls the range of test we are able to work with. So if you look at the PA8000 package, it includes a small, a medium, and a large ball bearing to strike the surface with. And if you were to specify up in Olson instruments, they've got a general purpose impactor, an automatic solenoid impactor, or a ultra thin one. And if you need to do up to the maximum range of the test, you wouldn't use any of these. You'd actually go and get a more substantial round-headed hammer to strike the element with. So just some general broad ranges is if we want to do the very thinnest tests, you need to use the smallest impactors, and the bigger the impactor, the thicker the element you can test, but the less appropriate it will be for very thin elements, because the frequency induced will be more broadly suited to a thick, a medium thick, or a very deep test, depending upon the size of the hammer. So once we've got that frequency chart, the most typical interpretation is based upon either a deviation of a typical frequency result or the measurement itself going wrong in very disrupted areas. So the most typical way to do an impact echo test is to establish a typical frequency, maybe presented as a typical thickness over your plate element, your wall or your floor. So in this case, a single frequency response without too much other input, around 7,500 hertz. And if we then go and test over delamination or over a large open void or void former, we're essentially testing a thinner element. So we go from maybe 250 millimeters thick to 100 millimeters thick. So we see a frequency change where the larger void, where that void reduces the overall apparent thickness of the element, and the frequency goes high. We go to the right of the keyboard to the higher frequencies. Now, if we get into the region of small deviated voiding, one possible output we could get is multiple frequency. Now, this is, I've encountered in real testing, less common, but it's certainly possible if we get voids close to the surface or we get quite disrupted areas, we might ruin our chart, no longer have a dominant frequency measurement we can see. But I'd rather show you some examples of the more typical ways we see frequency shifts, because that's the more common interpretation, is to go from one frequency to another in the regions of defect. So in this first example, this was on a concrete slab next to a boat ramp. So the concrete thickened as it went further along the boat ramp, as there was more distance to cover. So we measure the frequency as normal. We convert to a thickness, so 7,000 hertz, 250 millimeters in this example. In the example chart below, in this case, our thicknesses started around 0.5 meter and extended out to maybe 650 millimeters, so another 150 millimeters deeper. And we can see that we just had a very clean shift to a lower frequency to the left of the chart, so a thicker element from the left of that boat ramp slab to the right. And the data was done on a grid just to make the visualization easy for this example. So that's detection of thickness, a shift in frequency to the right of the chart as a higher frequency as the thickness decreases, or to the left of the chart, a lower frequency as the thickness increases. If we, again, complete our test over an open void or a void former or a substantial flat delamination, our most common output is an apparent thinning, a higher frequency result. One thing you'll find is that you'll typically chart your impact echo results in thickness, where your main interpretation is for thickness, but it can be more appropriate to chart frequencies opposed to thicknesses when you're looking for voids, because it can be hard to explain. Yes, this slab is all 250 millimeters thick, but this section I have labeled at 90 millimeters is not actually 90 millimeters thick. It's the region of my void. And this actually becomes even more important when we go to the influence of pore consolidation, which you might hear called a redshift. We actually, because of the hollowing effect, have a lower frequency. So the hertz reduces and the apparent thickness measured increases. So that can be very hard to explain to a client. Yes, you needed a 250 millimeter thick slab. We did a test and we've got some honeycombing over here. It's the region that I have labeled as 300 millimeters. It's hard to explain, but if you instead say we have a 7,000 hertz frequency, and in this region with a 5,000 hertz frequency, that's our defect, that's a little bit more easy to explain. So that's more appropriate. Finally, something worth pointing out on the devices we use is, while we do chart them out like in that chart of thickness over distance here, it's not always the case that the origin is the point of the test. So in this example, this test is at a 10 centimeter and 20 centimeter position, and the first test would have been completed at a 5 centimeter x 5 centimeter y position. So always be mindful of the real distances on your charts when using a setup in this. And if you wish to recreate that in other techniques, there's the ability to set a start distance from the origin in software for, say, Olson Instruments CTG2. So that's the conclusion I have for my impact echo theory presentation today. I'd like to thank everyone for joining me, and it's a good chance for any questions or thoughts we have before I wrap up the webinar. And thank you for coming along. Okay, so we have a question from Luke. What type of response would you expect to see from freeze-thaw affected concrete that contains small microcracks lowering the stiffness of the material? Would that be a low wave velocity, no response due to attenuation, or a reflection of the first shallow microcrack? Overall, do you think this is an appropriate test for freeze-thaw degradation in a 100 millimeter thick panel of originally 25 MPa concrete, on the theory of using a known thickness to find the inferred hardness? So it's actually What you've given me there, Luke, and you're welcome to unmute if you'd like to. We can discuss this in person. Is a lot of very specific facts I can't give you an answer on. So particularly, you said, find the inferred hardness, microcrack. So you've put a lot of certainty on that, where going beyond the basic theory of impact echoes. Tell me a little bit more about it, Luke.
Can you hear me?
Yes, I can.
Great. This is for my uni project. I'm
Sure.
doing some analysis on freeze thaw and flume walls. I'm trying to look at different methods for detecting empirically this degradation. I think this would be a good method. I was wondering what your thoughts were on those things.
My thoughts are, firstly, yes, it probably is a good method, but your role in research is going to be more able to answer some of the questions about what happens. Something that we always do with non-destructive testing, if you haven't done a lot of this kind of testing before, is sort of try and compare a known situation to an unknown situation. So maybe the structure before the freeze thaw damage to after the freeze thaw damage, and look for what change will happen. Now, if I was going to theorize what's going to happen, I think you're right. I think we'd see a change in the frequency. Now, so you see, I do think we'd see a change in the frequency due to the cracking induced. The first thing I'd like to put out is, would that be a low wave velocity, no response due to attenuation, or reflection of the first shallow microcrack? Okay, so the reflection is probably impossible for this kind of test. That would be so close to the surface, if I understand your geometry correctly. It'd be more an influence on the test than a change to the test. So sort of think of it like that honeycomb example, where you're doing something to the bulk of the concrete, and you're using a test that isn't up at the 100,000 to million hertz responses, which might detect a microcrack. You're using frequencies that are going to be mainly trying to assess the whole panel, the 100 millimeter thick panel. Low wave velocity is probably part of what causes a change in frequency when things deviate, but we refer to our results in terms of frequency. So we use an assumed velocity, which means we find results in change in the measured frequency. So your results are going to be in terms of frequency, not velocity. We only consider velocity when we're converting to thickness, and you wouldn't convert your measurement to thickness in this case. So the effect of lowering the velocity would probably be a reduction in frequency, but we measure frequency. We don't consider velocity in this case.
Yeah, I think it's baked into the formulas. You could probably kind of work it back out if you knew the
exactly right.
thickness.
Yeah. If you knew the exact thickness, you could, and if you knew the thickness, you could work out your velocity. So yes, that's one way to put into it. Do be aware that on these panels, you need to be tested quite reasonably centrally. But yeah, look, I think you probably see a deviation in frequency. I don't think you're going to lose the signal entirely, unless the entire thing becomes essentially so patchy that the signal doesn't travel. Then your test would fail. Something which which is always worth being aware of. We're expecting a certain kind of resonating response, like something which we can measure the dominant frequency of. If your panel deteriorated below the point where we could take that kind of response, we wouldn't be able to do a sort of quantitative change in frequency measurement. We'd just be able to see after 100 cycles, say, the entire thing's powder, and I can't test it anymore.
Yeah. Okay. Thank you very much.
Is that helpful, though? I mean, again, I sort of, what you must understand is I've presented in less than half an hour, about a little more than half an hour, a pretty basic theory overview of this technique. If you're doing research, do go read the standard. Do go do some background reading in signal analysis, because this is where these techniques come from. So when I'm talking frequencies and filters and all that sort of stuff, that's signal analysis. If you don't want to learn signal analysis, go and become a music producer as a hobby. That's even better. You'll understand it much more cleanly. But that's where all of these techniques come from, and all of the American standards that describe how they work. It all starts with using a particular sensor to collect a signal, and then using signal analysis processes to get to an output for it. And that will give you the background to really understand this. and maybe also to develop a more esoteric measurement for yourself if you're doing something like maybe some UPV testing or some other sonic or seismic tests on your panels. It'll give you the background to know what each of them is doing and how all of them come from the same physics.
Okay, cheers, thank you.